This lesson is about multiple binomial probabilities. Up until this lesson, all we've been doing is finding like probability of maybe getting 2 and just applying the binomial probability formula. Okay, in this lesson we'll look at things like what's the probability that our random variable is more than or equal to 2 and looking at that range of expected outcomes. So just the intro, I guess, where we're going here. So through example, if x is the number of boys in a family of 4, the binomial probability distribution, it'll be this table. Okay, we could have drawn the massive tree diagram for it to get these probabilities. If I'm after the probability of having at least 2 boys, that means that my random variable needs to be at least 2. We would find that probability simply by adding together those three probabilities. So the probability of getting 2, probability of getting 3, and probability of getting 4. And we could read these off our table, which would have been developed through a massive tree diagram. So it would have 3 on 8 and a quarter and a 16th. Okay, and I'd end up getting 11 on 16 as my answer. If I'm not provided with that table, so without constructing the table, this can be achieved using binomial probability formula multiple times. So if I'm after the probability that the random variable of number of boys is greater than or equal to 2, I'll identify that the number of trials is 4, my probability of success is 0.5, my probability of failure is 0.5. I think, okay, greater than or equal to 2, that means either 2 or 3 or 4. And I'll have 3 binomial probability formula calculations in here. So first one, 4C2, probability of success to the power 2, probability of the failure to the power 4 minus 2. And do the same thing for 3. And then the same thing for 4. And then I'll end up with 0.6875. And if I put 11 on 16 into my calculator, I'll see that these two are the same. So using the binomial probability formula multiple times is okay and looks pretty good. Alright, so that's a quite simple case. In some more complex cases, we won't want to do this. Okay, for example, find the probability of obtaining at least 2 heads when flipping a coin 10 times. At least 2 heads means the probability that I have at least 2, exactly the same as before. To do this, I would have to find probability that x equals 2, 3, 4, 5, 6, 7, 8, 9, 10. I would have to do 1, 2, 3, 4, 5, 6, 7, 8, 9 binomial probability formulas, and I'll probably make a mistake. Okay, or spend all my time in the exam just doing one question. So the way around this is to use complementary probabilities. So I notice that greater than or equal to 2, this is like at least 2. I could rewrite this as not something. At least 2 is the same as not 0 or 1. Whenever I have not, 1 minus, and I'm subtracting probability of it being 0 or the probability of getting 1 head. Okay, subtracting both of those from all the likely outcomes. So instead of having to do 8 or 9 probability formulas, I've only got to do the 2. Okay, so I'll have 1 minus and put it in brackets because I'm subtracting both of these. Now before I use the formula, I'll state the facts. So there's 10 trials, probability of success is 0.5, probability of failure is 0.5. 10, C0, 0.5 to the power 0, 0.5 to the power 10 minus 0, plus 10C1, 0.5 to the power 1, 0.5 to the power 10 minus 1. Okay, and mash all that into your calculator. Even doing that was a bit of work, but I got 0.989. Just think, is this realistic? Okay, I'm flipping a coin 10 times. What's the probability of getting at least 2 heads, so 2 or more? I'm probably going to get that on pretty much every scenario. Okay, it's pretty likely that I'll get at least 2, flipping it 10 times. Okay, so let's try see what this other one is. So find the probability of obtaining no more than 8 heads when flipping a coin 10 times. Alright, so probability of no more than 8. So this is my random variable being no more than 8. So less than or equal to 8. Okay, no more than 8. Got the same problem here. I'd have to do probability of 0, 1, 2, 3, 4, 5, 6, 7, 8 if I was just to do that directly. I want to use this complementary idea, flipping it around. No more than 8 means not 9 or 10. Okay, so there'll be 1 minus probability of getting 9, or the probability of getting 10 heads. Again, list these things. 10 trials, success is 0.5, failure is 0.5. Okay, and I can go ahead and substitute those values in. And now it's just calculator time. I end up with exactly the same result as before, 0.989. And you should be able to think about why they're exactly the same. Okay, think about the symmetry of this distribution around 5 heads. Okay, and it should make sense. Alright, so what about this last one? Probability of no more than 5. So probability that x is less than or equal to 5. So no more than 5. If I was going to do it directly, I'd have to do 0, 1, 2, 3, 4, and 5. Too much effort. What happens if I flip it around? No more than 5 means not 6, 7, 8, 9, or 10. So even using complementary probabilities, I would have to be subtracting probability of x equals 6, probability of x equals 7, all the way up to probability of x equals 10, which would be far too much effort. What we can do alternatively is use our graphics calculators. So on the next page there's some instructions for you on how to do this, but I'll give you a walkthrough right here. I'll go into my stat mode. I'm talking about a distribution. It's a binomial distribution, and I'm after more than one probability, so cumulative probability. Okay, I change this list to variables so I can input one value. I want x is less than or equal to 5. So this BCD mode does always less than or equal to. So I can put my 5 in here, 10 trials, probability of success is 0.5. Go ahead and execute this. Get 0.623. So the probability that x is less than or equal to 5 is 0.623. Key thing to note with this graphics calculator is that whatever you put in this x column is x is less than or equal to that value. You can't put greater than or equal to or anything like that. Always just less than or equal to. So it's really important that you note that. Let's just see if we can verify one of these other examples. So for example, probability that x is less than or equal to 8. I should be able to put an 8 in here because it's less than or equal to 8. And hopefully, when I execute, I'll get 0.989. Phew, that was close. Okay, so that's the whole idea. I can't just put a 2 in here, like for this first example. Okay, that'll be no good. Okay, if I wanted to use my graphics calculator up here, I'd have to write 1 minus the probability of x being less than or equal to 1. Okay, and this can go into my graphics calculator. Okay, so when I do this, I'd write from graphics calculator. Okay, so over the page is just the instructions on how to use your graphics calculator, and this important note that it's always in that form. Did we verify this one down the bottom? Yep, probability of obtaining at least 2 heads when flipping a coin 10 times. Okay, so that's one I was talking about, where it's probability of x being greater than or equal to 2. And we need to change this to 1 minus the probability of x being less than or equal to 1. Always needs to be less than or equal to. I would put this into my calculator with a 1 here. Lots of clicking. I get 0.0107. Okay, and subtracting here gets me my 0.989, just like I got when I did it directly. Okay, so the graphics calculator will really help you out here. If you have to do more than, say, 2 or 3 probabilities, do it on your graphics calculator. Okay, there's a whole heap of questions for you to practice.